All right. Welcome everybody to today's seminar. It's absolute mention pleasure to have Yonina Eldar visit us. She held the chair in the Weizmann Institute in Israel. She was previously held the chair in Iran. Yonina is an amazing person. She runs the full gamut from statistical and signal processing and sensing all the way through to devices in such a broad gamut that we could literally spend the hour just listing the awards that she's won, which in themselves are also impressive because they cover everything, the teaching awards as well as all of the work for the awards for her work. She's fellow at the IEEE, fellow at the Trinity there's a whole list you can go over afterwards. But rather than waste your time listening to me, instead I prefer to give it time to you. So,
thank you so much, Ken, for that really thank you so much for that super kind introduction. And I have to say, it's just amazing to be here. So I visited here a few years ago, which was also impressive, but seeing all the amazing activity that has been going on here in recent years, I really feel like, like a child in a candy store with so many great things. So thank you so much. I want to thank everyone who helped organize this day, and in particular, Joseph and Ken and Koshik who put this all together. And I feel like I've been treating like royalty. I have an amazing schedule and just all morning seeing all the amazing activity going on here. So let me say before I begin, my motivation to be here is really, of course, I'll tell you what we do, but really to look for collaboration opportunities. So if there's anything in the talk today, and I'm going to cover a broad spectrum of activities because I imagine that people here have a pretty broad background. So if there's anything that you'd like to learn more about, I'm still going to be in the area for another week and a half or two. And of course, we can always do things over Zoom. So please do feel free to reach out. And I'm really excited about potential collaborations here. So with that, let me begin. So what I want to share with you today are ideas that we, and of course, many others in the community at large and here as well have been working on, and how we can think about sensing in more efficient ways. And by efficient, we mean, we want to do less data rate, less bit rate, less latency, less power, but, better resolution, better sensing abilities, etc. So what I'll share with you are some ideas that we've been working on in, kind of over the past decade with more emphasis on the more recent ideas and how we may be able to do that. And we'll go through some of the theoretical concepts. Of course, I won't go into detailed math. All of that is more in the references, but just to give you an idea, as well as different applications to different areas with the hope of finding, other applications that we may be able to consider together. So, if we look today at how things are moving, we know that today we're generating more and more data, right? I mean, the push in almost every area is get as much data as you can. And this, of course, comes with various challenges. So first of all, we have to store all of this data. And, this is just one example. I looked online, there's 3 million data centers. I mean, it's a crazy number, right? So you have these huge buildings that are basically storing bits, right? So, you have to do something with all of this data. That consumes a lot of power. Communicating it is a challenge in terms of power, latency, and many other limitations. And, this was a prediction a year ago, which of course ended up being more than they predicted. These are numbers that you can't even, at least for me, I can't even comprehend, right? Like the internet traffic exceeded a zettabyte. What does that even mean? To the power 21. These are just, extraordinary numbers. The power associated with the IT industry is larger than the power consumed by some big countries, right? So, these are things that we have to start worrying about now that we're taking so much data. And the question is, do we really need all of this data that we're taking? Now, why would we think otherwise, right? Why would we think we could get away with less data? So if you look at some basic applications, and these are some of the applications we've been working on, let's look, for example, at medical imaging. So if you look at an ultrasound device, it's basically like a MIMO radar, right? It has tens of antennas. They're all continuously collecting analog information. And at the end, all of these, 256 analog channels at 50 megahertz are projected down to terabytes of data that are projected down onto a single, pretty lousy image, by the way, for anyone who ever had an ultrasound scan. And that's what the doctor uses to make a decision. So one of two things are happening here, right? Clearly, right now, we're not using the data we collected. So that's kind of, question number one, do we actually need it? Question number two, if we are taking it, then we should be using it and not just creating these lousy looking images, right? So these are kind of, some of the ideas that we've been looking at. There's of course more obvious applications. If you look at smart cities or autonomous vehicles, again, the push is let's put more sensors, collect more types of data. but we're not actually using them when we're making decisions. And probably the most obvious example today are deep networks, right? We know we could build amazing deep networks, let's say classification networks, we could distinguish between dogs and cats, and of course, more challenging problems too. But we need millions and millions of examples in order to get that right. Whereas a child could see, one or two examples of a cat and a dog in a book and recognize a cat and a dog on the street, right? So clearly we're doing something wrong. We're not collecting data in the ways that are necessarily the most useful for us for actually extracting the information. So sorry, I keep going backwards on the pointer. So the question is really, is there a way to acquire and process only what we need? And that's kind of been a theme in our group.
Analog girl in a digital world.
That was, I see the question, is the sound better? Well, that was definitely loud, but all right. So this is a cool song by Judy Foreman, who's a pop singer, not an engineer as far as I know. And she has this really cool song about being, an analog girl in the digital world. And we know that today, of course, more and more, essentially almost all of the processing is being done in digital devices. But this again comes with a price. So we have to convert our data to digital. And of course, everyone here knows the basic principles of doing that. We sample in time, we then quantize, but that has various bottlenecks associated with it that we're going to highlight. So today, all of the sampling and quantization is done by at least the sub-Nyquist theorems. And in fact, if we look more carefully at how systems are built today, they're still built in a very modular fashion. So what I mean by that is that, let's say we have a radar system or an ultrasound system or a communication system, right? So we have, the transmitter is going to transmit information. At the receive side, we basically break down our processing chain into these individual blocks. So we first sample, convert this incoming signal we sample it in time, and that is always done at the Nyquist rate or higher. We then quantize, and that's done, based on rate distortion principles. So kind of roughly speaking, we get 6 dB per bit. So, depending on the SNR that we want, we could determine a number of bits. And only after we've sampled and quantized, where this is where a lot of the hardware and power go, do we start thinking about our specific task, right? So if it's ultrasound or radar, then typically we're going to be doing beamforming, which means we take a lot of channels and we point them in a certain direction. But the fact that at the end we're only getting a projected image is not taken into account anywhere at the front end of the system. Okay, so you see that things are built in a very modular fashion where each block is optimized separately, independent of the end task. And here I'm not talking about, one system that has multiple tasks. We're talking about a fundamental task like radar. Radar is always going to give delayed Doppler maps. So it's not a task in a specific application, but rather the entire system is always going to be looking at that particular task. Now, this works, of course, because our systems work today, but it comes with a price. So as we're looking at, high rate communications, definitely terahertz, high resolution, if we're looking at radar or other sensing devices, this means that we're going to have to be looking at higher sampling rates, higher bit rates. This causes, a lot of latency in the system. And as we said before, it consumes a lot of power. If we look at medical imaging, which is something we've been working on a lot in our group, then this has other trade-offs. It's not just hardware. It means that we have to scan for longer times. It means that we have higher radiation. So at the end of the day, this conversion from analog to digital and the processing in digital creates bottlenecks that are starting to become very important when we look at modern systems. So what can we do differently? So a lot of the work in our lab has been focused around designing systems in a unified fashion, so not optimizing the blocks separately. And in this joint design, there's 3 important things that we take into account. So one is structure, okay? Now structure could be a lot of things. It could be things like sparsity that I'll mention briefly. That's kind of older kind of approach, but there's more elaborate forms of structure, wave equations, anything that's governing the system. It could be structure in the system, or it could be structure in the input. So that's one thing that we want to take into account. The other, of course, is the task. What is the system designed for? And it could be that the task is actually a very low-dimensional one, and therefore we could reduce a lot of the blocks in the system. And the third is not really an independent concept, but I highlight it because sometimes it's counterintuitive. And that is that the output of the system does not have to be informative by looking at it or by listening to it, right? We could do processing. So all we need is, from an information theory point of view, for all of the information to be there. It doesn't have to be easily accessible as long as we have an algorithm that knows how to extract the information. And you'll see how that comes into play in the different systems that we design. So here I'm focusing on analog to digital on the sensing part, because, I know we're at the wireless group and there's a lot of hardware being done here, but the same concepts are concepts that could be used in purely digital systems. So we've been doing a lot of work in our lab in the past years and using these same principles for purely data-driven systems, machine learning tasks, and again, exploiting these same ideas of modular design, non-modular design, holistic design, exploiting structure and task, also in purely data-driven systems. And these are two recent books. They're edited books, so they of course have contributions from many authors, but within it, we also talk about these principles in purely digital systems. Okay, so using these ideas, we could design systems that have several different advantages. So we could get, more compact portable systems with high quality. We could, like in medical imaging, we could have fast and quantitative systems. We could get actually quantitative parameters, not just qualitative parameters. Of course, we could build high resolution radar, microscopy, ultrasound. We'll go to some of these applications. And like I said already, we can also use these in purely data-driven systems to get more efficient deep network systems as well. So hopefully that gives you a sense of kind of, what I'm going to be talking about and the common thread to the different topics. Depending on time, we'll go through the three kind of thrusts: how we exploit structure, how we exploit the task, and then, how we exploit this also in a digital setting in more AI-based systems, and go through some applications. But I do want to say, I probably have more slides than I could actually go through, and that's a weakness that I always have. So I will try very hard not to talk super fast. But instead, if there's questions, feel free to ask. I mean, we could skip an application or two, but make sure that everybody's kind of following. So feel free to ask questions as we go through. All right. So any questions so far? Okay. So let's start. This is kind of older work, just to kind of set the stage on how we could exploit structure in the form of sparsity, and then we'll see how we move forward to some newer ideas. And what you see are on the slide are different systems that we've built on the lab that are kind of using these ideas in practice. So when we started looking at this, over a decade ago, some of the applications that we looked at where there's natural structure, but in the analog domain, not in the digital domain, is, for example, this multiband problem, which of course is still relevant today, where we have a wide bandwidth. We have several users on the channel. Each one of them is narrowband, but they're spread over a wide frequency range, and we don't know the carrier frequencies. Of course, if we know them, we could just demodulate them one by one, right? But if we don't know them, we can't do that. And therefore, of course, the traditional approach is to sample at Fmax, which would be the Nyquist rate. But that's just intuitively wasteful, right? Because there's obvious structure here. The question is, how do we capture that structure, and how do we use that to build more efficient systems? So let me just say that even though here we're focusing on a communication problem, the same ideas are true in many imaging applications, and we've used these ideas in various imaging applications with multiple multispectral applications like multispectral imaging or multispectral CT. So here there's obvious structure, right? The question is, how do we model it mathematically, and then how do we exploit it? A different form of structure that, again, we've used a lot is the structure that we see in radar or any time of flight system, where we send a pulse, and what we're receiving are basically reflections of this pulse every time it hits a target. So in radar, you send a pulse. When it hits a target, it will come back. What you want to figure out is the time of arrival, because that will tell you the distance to the target, and the amplitude, because if you look at the amplitude over time, you could recover the Doppler, right, or the velocity of the target. So this model, of course, appears in any time of flight system like radar. It also appears in ultrasound, which is an area you'll see more of throughout the slides because we've been working on a lot. So ultrasound works the same way. You send a pulse through the probe, you're receiving reflections of this pulse as it's propagating through the tissue. The challenge in ultrasound is that, first of all, it's more like MIMO radar. So the probe itself has anywhere between 128 and 256 elements. The other thing is that it's near field, okay? So mathematically, it's a little bit more challenging because you have to do the beamforming, you actually have to do this on a nonlinear grid. So it makes it more challenging, which is one of the reasons that people actually oversample quite a bit in ultrasound, because you want to be able to do small time shifts for beamforming on a nonlinear grid. Again, this is kind of challenging to do. So people sample at a high enough rate that time shift will just correspond to some other point on the grid. Okay, and that's why the sampling rates in ultrasound are so high. So the challenge in these types of problems is to exploit the structure, not only to sample at a low rate, but actually to do the processing at a low rate. And this is very important in everything we're going to be talking about today. I'm not interested in just getting an efficient front end and then having to interpolate back, right? Because I'm interested in the entire system performance. So we have to somehow, sample at low bit rate, but be able to do the processing at the low rate itself. And that is something that is more challenging. So particularly in ultrasound and radar, we worked a lot on what we call compressed beamforming. So it's not only the sampling rate that's reduced, but also the whole processing chain is done at the low rate as well. And we'll go back to that later on in the talk. So I'm not going to go into any deep math in this talk. And again, I trust me that there are, equations behind everything, but this is probably like the only equation on the slides, and there isn't even really an equation here. But those of you interested in the math could, find it all in the references. But just to give context, so we looked at 2 examples. There's many more examples of structure. And what's nice is that mathematically, they could all be described in a unified way. So we can show that all of these examples could be described by very, very simple mathematical structure, which is a union of subspaces. So what that means is, we're used to, most of signal processing is operating in a subspace. Okay, so we're used to doing subspace processing. But what a union says is that we know that a signal lies in a subspace, but we don't know a priori which subspace. So we have many options of subspaces. One of them is the correct one, but we don't know which one. Okay, and that is actually, you could convince yourself quite easily that that's actually a nonlinear model, so it's a little bit more involved. You can replace subspaces by manifolds and almost everything carries through. And the important thing that we can prove is that if your signal lies in union, the rate at which you need to sample the signal or to represent the signal is the rate associated with the sum of 2 subspaces in the union. So I can have, infinitely many options of subspaces, but the rate is dictated only by the sum of 2, or at least that's what the lower bound says, which paves the way to sub-Nyquist sampling, which means that at least there's potential to sample at a low rate because the Nyquist rate is the rate associated with the sum of all subspaces. Okay, so I went from all subspaces to 2, and if there's many options of subspaces, then I have a great saving. Okay, so but this is just the bound. The question is, how do we achieve it in practice? And over the years, we've developed different systems in the lab that we were able to prove over the years that we could actually always use them to achieve this minimal rate, and that's this sampling paradigm. So the idea is, I think, intuitive. What we could, and again, we could prove this formally as well, is what we do is we take our signal, we multiply it with a periodic function. Now, as you know from basic Fourier analysis, if we have a signal that's periodic in time, in the frequency domain, it's always going to look like a delta function. Okay, it may have different amplitudes, but it would always be a delta train. And if I multiply in time, I'm convolving in frequency. So what I'm doing, let's say with this multiband signal, if I'm convolving in frequency, is I'm taking this, I'm shifting it all the way to the right, shifting it all the way to the left. Sorry, there, shifting all the way to the right, shifting all the way to the left, and summing up. Okay, so I'm creating aliasing of the data. And then what we can show is that we only need to take kind of one window of this alias data, and that will be enough to recover the information. So basically, for those of you familiar with compressed sensing theory, what we're doing is we're not using compressed sensing to sample because this is an analog problem. So we're using analog components to alias or mix the information. But then in the digital domain, after we've mixed it, we can show that we could recover the correct subspace using compressed sensing ideas. And you'll see later on throughout the talk that this notion of mixing information before we do something is actually very useful for many other problems, not just for low rate sampling. So we'll use the same concept for low bit rate, for low latency, for security. I mean, that I'm not going to show here, but we've done it also for security. So this notion of mix and then reduce something is actually very useful, not just in the presence of sparsity. Okay, so those of you not familiar, let me ask. Who is familiar with compressed sensing? Okay, so a fair amount of people, but let me give you a very compressed version of compressed sensing. And those of you who have not heard about it, it for a while has been, before AI, that was like the signal processing hype was sparsity, and everybody was working on sparsity. So you can find many tutorials online, but it's actually super useful. So the idea behind compressed sensing is that if you have a vector that is sparse, meaning it's long, but it only has a small number of non-zero values, or it has a small number of non-zero values in an appropriate basis, then what you can show is that you could recover it from a small number of measurements. So if the length of this vector is n, I don't need n measurements. I only need on the order of k log n measurements. But of course, those measurements have to be taken carefully. And basically, they have to be mixed versions of X. So we use a matrix that looks like a random matrix. It doesn't really have to be random. It just has to mix the information enough. And we could prove, not we, Donahoe and Contes and others have proven that you could recover the sparse vector from this short measurement vector, and you could do it in computationally efficient ways. Okay, so what we do in the problems we're looking at, we don't necessarily have sparsity, right? The data is not necessarily sparse, but we have a low-dimensional representation. So what we do is we do this aliasing and mixing in the analog domain, and then we use compressed sensing to give us the correct subspace. And once we have the correct subspace, we use standard recovery methods within the subspace. Okay, so does that kind of make sense on a high level? Okay, great. And then we could apply this to many different structures, not necessarily sparse structures. And I just want to point out that, the basic vanilla compressed sensing is what I showed before, this nice linear model. But over the years, many people have looked at, various different extensions of compressed sensing. In our group, we looked a lot at nonlinear measurements because we were working a lot in optical problems where the measurements are nonlinear. We've been looking at, statistical sparsity, so structure in the statistical domain, not just in the signal domain, tracking, etc. And there's also, of course, like in any other field, a lot of work recently on how to use deep learning techniques to recover sparse vectors, not just kind of standard L1 optimization, etc. Okay, so that was the aspect of exploiting, various forms of structure beyond sparsity as well. The other thing that is very important, especially when we look at 6G signals, which is another aspect that we're looking at a lot in wireless networks, is that signals today could have very, very varying dynamic range, especially when we're looking at combinations of signals. So if we're looking at, integrating sensing and communication or integrating, humans with devices, these are going to come at very different dynamic ranges. It's not just these standard point-to-point systems where you have power control and everything is kind of dynamically flat. So how do we accommodate for high dynamic range? Now, the tricky thing about this is that when you look at papers, it's not an issue, right? Because in most papers, ADCs have infinite dynamic range, right? But in practice, they don't. So in practice, any ADC will have, some finite dynamic range, and if a signal goes out of the range, then it will be clear. So how could we overcome that? And here we use, Here we use, similar ideas to compressed sensing, although this has nothing to do with sparsity, with this notion of aliasing. So what we can prove is that if you take the signal and you wrap it around, so you perform a modular loop. Okay, so let's say I have a device and I know its dynamic range is fixed to some minus lambda to lambda, because that's what the device could do. Then what we could first prove and then build is that if we do a modular operation to the signal first, so we alias it within the range, we could recover first mathematically, we can prove that there's uniqueness and we could recover the underlying signal. If the signal is band limited, then we could do this at the Nyquist rate. And if the signal has structure, we could do this at a sub-Nyquist rate. So we could get the same sub-Nyquist rates we showed before, but now we can accommodate high dynamic range. Okay, so we could prove that this works, but we also actually build the board that does it, and we can show that this is very robust as well. And the nice thing is that this a priori has nothing to do with sparsity, right? We're not exploring sparsity here, but what we can show in the actual mechanism in the algorithm that we use for recovery is that we do break up the signal into a signal part and a sparse part, where the sparse part are the jumps, right? Every time it's going to hit the lambda and fold back. And we actually do use, at least mathematically, ideas of sparsity in order to be able to recover the signal, although there's no sparsity assumption on the signal itself. So it kind of does connect to those earlier ideas. But this is very important practically, because now we can accommodate very nicely high dynamic range signals, and we could build this, and it's pretty robust. I mean, at least in what we've done so far, it works quite well in practice. It also, of course, allows us to reduce bits, not just sampling rate. Okay, because if I limit the dynamic range, then I need fewer bits. So, that's kind of one thing that we've been working on. And then the last component that I want to mention on the ADC level is the clock. So, power in the ADC goes, into various components, but one of them, of course, is the sampling rate and bit rate, which we addressed. And then the other is just the notion of having a clock. So the other thing we've been looking at, this is particularly for health applications like ECG monitoring, or areas where, most of the time nothing really bad is happening, right? But once in a while, there is something happening that you want to know. And, could you capture that in an asynchronous way? So here, what we've been looking at is looking at asynchronous ADCs, or time-based ADCs, where the idea is that instead of having a clock and sampling, the amplitude at every specific point, what we're going to do is we're going to integrate the signal, and we're only going to sample when the integral passes a threshold. So basically, we're only sampling when something happens. Okay, and when nothing happens, we're not sampling, so the integral is just going to be low. And every time the integral passes a threshold, we sample. And again, we can prove that from those samples, we could recover the signal. And as before, we could recover them at a sub-Nyquist rate as well. So putting it all together, we can now accommodate high dynamic range. We could build asynchronous systems for, again, and that's not bad. You don't need that in every application, but let's say in health monitoring applications where, again, most of the time nothing is happening, that could be very useful from a power point of view. So putting that all together, that's kind of the first part. We could exploit structure, we could exploit we could overcome high dynamic range, we could do low power systems. And the important thing is that we could do this in practice too. It's not, we could prove the theory, but we've also built the systems, and you see them here on the slide, that could actually do this all in practice. Okay, so before we move on to some more detailed examples, questions on anything so far? Yeah.
One question, you showed an example of how you could do clock sampling as well. Would this work also for a real-time system, or must this be when,
Oh, it's totally real time. It's totally real time. So it's as real time as a Nyquist system.
I see.
So Nyquist isn't, so strictly speaking, Nyquist isn't real time, right? Because to recover every point, you need infinitely many samples, right? So in some sense, this is even more real time because I'm accumulating the samples, and I could do like a moving window type recovery. But it would be the same real time as Nyquist is. Okay, so let's take a look at some concrete applications before we move on to further ideas. So one of the things that we've been working on a lot in the lab, and for me personally, I like this application because it's a medical application. So I'm going to show some ideas in ultrasound, but everything we do in ultrasound is the same in radar. So ultrasound and radar, from my point of view, from a mathematical point of view, are very similar systems. So one of the first things we've looked at in ultrasound is saying, okay, putting these ideas together, we should now be able to sample at very low rates. And surprisingly, at least to me, ultrasound systems today are still analog, meaning the probe is totally analog. You send a signal, you receive one back, it goes through an analog cable into the machine, and only in the machine is it sampled, digitized, and processed. Why? Because of the high rates, right? Because you can't sample at terabytes within the probe. Okay, going back to the discussion we were having this morning with sampling at terabytes. So there is no way to do that today within the probe. Now, once we can sample at low rates and low bit rates, we could do it directly within the probe. And basically, I don't need a machine, right? So I can take the data, send the data wirelessly to anything, right? So the doctor could be holding an iPad and seeing the result. And the cool thing is that now I actually have access to the data. So today, in ultrasound machines, you only have access to the image. You don't have access to the data. Okay, so why is that useful? So
everybody, I would like to show you here a demonstration of a normal heart. What we can see here, radiography of the subject's heart. We can see a 4-chamber view in which we can see right now.
Okay, so this is a demo from the lab. The data is going directly from the probe to the local machine, to the remote machine in the lab, and soon you'll see him scan into an iPad.
Valve. We can see the nice motion of the leaflets.
This is just for power purposes, but the data is going to be there.
Function, and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject's heart.
Okay, now he's scanning directly to the iPad. So the first thing we can do is get rid of the system. Right now we just have a simple probe and an iPad. So that's kind of thing number one. The other thing we could do is that now we have actual access to the data. And this goes back to what we said at the beginning, are there better things we could do with this data? So the first thing we could do is we can say, ultrasound images are pretty lousy images if you've seen them, right? They're full of noise, like this type of image. So instead of doing standard delay and some beamforming, why don't we do something more elaborate? And specifically what we do in this case is what we call model-based AI. I'll talk about that more later. But basically we use a signal processing concept, but we use learning within the concept. So here we're using, adaptive beamforming, but we're learning the weights rather than keeping them fixed. And that already gives us an image with much better contrast and much better resolution. So we're basically using a system that's much easier, and we're getting a much better image because we're just doing better processing. The other thing we could do, and this is something we're kind of excited about, but needs much more exploration, is saying, okay, now that we have the data, why don't we try to get quantitative imaging and not just qualitative imaging? So ultrasound and radar today are super qualitative, right? I mean, you get an image and you can try to extract things from the image, but they're not actually going after the physical properties of the material. Now, we know these are wave equations, both in ultrasound and in radar. So what we've been doing more recently is saying, okay, could we write down the wave equations and actually try to solve for the physical parameters? So this is just a simple example. Okay, this is in a very simple scenario. It's not yet clinical data, which is hopefully our next stage. But what you see here is a conventional image, a Rehovot image, which is a conventional ultrasound image. And you can see there's something going on, right? I mean, there's these black lesions that may be suspicious, but you can't see beyond them. So this is a standard case where the patient would either be sent for a biopsy or sent for, some other imaging modality. But then if you take the very same data, and instead of doing beamforming, you solve the wave equations, here in particular, we're showing the speed of sound, then you can see that in this area, the speed of sound is very different, it's very high, and that's actually indicative of a tumor. Okay, so this is, of course, a naive example. Okay, it's not clinical data, it's simulated data, but it shows us the power of looking at actual physical parameters. So this is something that we're excited about. And again, one of the challenges is solving these wave equations in real time, which is quite difficult. But here again, we use model-based AI ideas. So basically, we have a model, we use it, and we use the power of AI to learn the parameters more efficiently. And the way that we could generate data here is just by simulation because we have the wave equations. So that's kind of what we've been doing in the ultrasound domain, and everything we're doing in ultrasound, we can also do in radar. So I won't go into great detail in radar because they're really equivalent. Let me just show a beginning of a demo, and all of these movies are on my webpage. So if you're interested more in radar, you can find the information on my webpage. But again, radar is very similar to ultrasound. So the basic kind of trade-off that we have is between bandwidth and resolution. Traditionally, we need more bandwidth for data resolution, but that, of course, means higher sampling rates, etc. Same thing with Doppler resolution. If we want better resolution, we have to look at the target for a long time, which, of course, means we're not looking in other areas. And spatial resolution. We need more antennas if we want spatial resolution. And using these ideas, basically, we could break these trade-offs. So we could build a system that has low bandwidth, low sampling rates, small number of antennas, small dwell time, and still get very good resolution. So the way we do that is that instead of using the entire frequency, we only use a subset of the bands, but we can show that, again, with appropriate processing, and with noise and clutter and everything, we're still getting very high resolution delayed Doppler maps. And that means that if we're only using part of the bandwidth now instead of all of it, then we can coexist with communication channels, right? So we can now, look at the channel, figure out where the communication signal is, and transmit the radar only where the communication does not exist. We no longer need the wide bandwidth for the radar. So this also kind of paves the way to coexistent, but the mathematics is all the same as what I've shown before in ultrasound. We could do the same thing for reducing time on target. So instead of looking at one target for a very long time, we spread the information in multiple directions at the same time, but then can still extract each map separately. And all of this is real data. So there's noise and clutter and everything, and we can still get, very good performance. And finally, we can do the same thing in the spatial domain. Okay, so I'll skip that in the interest of time. So we've been looking a lot at applying these ideas, both of efficient radar and coexistence with communication in, automotive radar and autonomous vehicles, because there, of course, both sensing and communication are very important. So again, I'm going to skip through these demos, but you can find them on my webpage. We've also looked at using, small antennas that still get very good localization. These are some field experiments that we've done recently at Weizmann with the different antennas that we've built. So basically the idea is to use a sparse array, so we're not using all of the antennas, and each individual antenna, again, is sampled at a low rate, low dwell time. It's kind of putting all of these points together and still localizing the targets with very good resolution. Okay, so that's a little bit of what we've been doing on, on the automotive side. More recently, we've been really excited about trying to think of how we can use these ideas in health, also radar, not just ultrasound. So one of the things we've been looking at is vital sign monitoring. And again, it's the exact same models. So trying to, just stick a radar at the ceiling and monitor, different people getting their vital signs. And the reason that this is possible is because the signal being reflected is going, it hits the people's chest, and it's going to come back modulated. And of course, it's very fine modulation. So traditionally, it was thought that you can't get these modulations off radar. But again, using all the ideas we spoke about before, so the modulo ideas, the mixing, which gives us better resolution. Here, we're not trying to reduce sampling rate. We're looking at the flip side of that, of just getting better resolution. We're actually able to extract, the vital signs of multiple people We've been looking more recently at trying to do this through the skull. So our main achievement is the skull. It's not a person, do not worry. We don't do that to our students. But this is actually, we had a whole team of people just designing the skull. So if you look inside the skull, it's actually mimicked. We ordered it especially, actually cost tens of thousands of dollars. But my students laugh that it costs more than a human. But anyway, inside it has different materials that are supposed to mimic what we actually have inside our skulls, hopefully. And as you can see, we can inject different things into the skull. It's a very elaborate kind of phantom, which we kind of invested in. And now what we're trying to do is to see, could we use these ideas of radar to get a combination of what we did with quantitative ultrasound and radar. So we want to get quantitative parameters in order to be able, for example, to detect a stroke or something ongoing before you put the person under an MRI machine. So this is just the beginning of work. We have some initial results, but getting through the skull is a challenge. So I'm putting it out here because this is something we'd really like to collaborate on. What we have done so far, which is easier and more successful, is we've been looking at localizing gold nanoparticles. So if anybody here is working kind of in drug delivery systems, one of the ways that drugs in more modern medicine are being delivered is by tying them to these gold nanoparticles for chemical reasons. But that's great from a radar perspective, right? Because gold is a very good reflector. So we were looking at, could we monitor these drug delivery systems by using radar? And so far, what we did, so that's a cow's brain. That's easier to do, and it's skullless. So of course, if there's no skull, it's easier to penetrate. But at least what we've been able to show right now is that we can inject these gold nanoparticles into the tissue, and we could localize the gold nanoparticles. So this is the beginning of work, but ideally, we'd like to put it all together and be able to get quantitative maps within the skull. Okay, so shifting gears. That was more about, exploiting the structure, exploiting the moduli and all of the different aspects to get good resolution for localization. The next thing we'd like to do is to be able to exploit the task. Okay, so what do we mean by that? For example, if you think of ultrasound, right? At the end, I'm not interested in these individual signals. I'm interested in their combined output, right? So, could I exploit that to reduce rate? And that's part of what we already exploited in the ultrasound that we showed you. But we can think of other examples of tasks as well. So a very interesting one is quantization, right? All systems have quantizers. Now, of course, if I'm quantizing to 32 bits, then I can ignore the quantization. But if I'm quantizing to low bits, which is what we do in a lot of modern systems, then I'm going to have the error due to the quantization anyway. So when you think about it, I'm designing my sampler to have zero error, right? Above the Nyquist rate, so I have no error. But then I have huge error anyway because of the quantizer. So, that's completely wasteful. If I'm going to have error anyway due to quantization, then I reduce the sampling rate without having additional error. So, there the task is quantization. And there's many other examples as well. So I'm going to go through this, quite quickly. Again, I'm skipping the math, just trying to highlight the concepts. One of the first things we looked at, and I think there's a lot of potential extensions here, is looking at statistics. So there's many, many examples in array processing, for example, or in communications, where you're sampling data, but you're not interested in the data. You're going to extract moments from the data, and your processing is going to be based on the moments. So let's say covariance is a great example. There's many applications. In fact, in most applications of array processing, the processing is done in the covariance. So this raises an interesting sampling question of, if I'm going to sample a signal, but I only want to estimate its second order statistics, assuming it's stationary, at what rate do I need to sample the signal? And the answer is very, very low, effectively zero. So why is that the case? So let me just try to give you intuition on the back. So the idea is as follows. Suppose that we have, a sampling set. I have a signal that's band limited, and these are my samples. This is not going to be enough to recover the signal because it doesn't obey the Nyquist rate. But now, when I'm interested in the covariance, right, I'm only interested in the time differences because we know that the covariance, right, we estimate from the time differences. So I can construct a set with n points that if I construct it appropriately, it can have n squared differences, okay? So maybe n is below the Nyquist rate, but n squared could already be above the Nyquist rate. And if you take, right, so I have a savings here of a square root of n, and if you take n to infinity, right, I could drive my rate down to zero. Now, of course, in practice, you're not going to sample at a close to zero sampling rate because of noise, but it does indicate that you could reduce the rate quite substantially and still get good recovery of the covariance. So we can formulate this all mathematically. Let me skip that. I'll move to applications. So we've used this in a variety of applications where it's enough to estimate covariance. So one is, of course, going back to this cognitive radio problem. I'm trying to localize where there's users in the spectrum. And for that, it's enough to know the covariance, because if there's a user, then it will have a non-zero covariance. And if the covariance is zero, then there's no user, right? So we've used this, for example, to build, an efficient cognitive radio system where we sample at a very low rate and we could still estimate the covariance. And it's very, very robust to noise. So this is a signal that we built. The input has 3 gigahertz bandwidth, so 6 gigahertz Nyquist rate. And we sample at order of 300 megahertz, so only 6% of the Nyquist rate. And what you'll see next is that we can actually recover, where the signal is. And this is very efficient. We can do this in real time. You don't need a lot of samples in order to get a good estimate. So of course, when we subsample, we get an alias spectrum, but after the recovery algorithm, we can localize where the signal is. And again, there's, the movie show many examples. You can look at them afterwards on the webpage. Now, another application that we're actually quite excited about that has nothing to do with sampling is super resolution, but this is the flip side of sampling, and hopefully I'll show you why. So one of the problems that we've been looking at is this notion of super resolution in microscopy. So when you use an optical device, you're always limited by diffraction limit, which says that you can't see details that are smaller than half the wavelength you use for illumination. So if you're using an optical device, you can see cells and bacteria, but you won't be able to see proteins and small molecules, which is what people are interested in today. So in 2014, the Nobel Prize in Chemistry actually went to, these 3 important researchers, Betsy Helen Warner, who had a really, really clever idea of fluorescence microscopy, where the idea was, if you want to take one high resolution image, you can take thousands of exposures, where in each exposure, you make sure that there's only a small number of fluorophores fluorescing. So think about it like you have an image, you put kind of fluorophores all over the place, but you make sure that in each exposure, let's say there's only 3 green lights, okay? And then if there's a green spot, you localize it. So you put a Gaussian every time you see a green spot, and then if you sum over all images, you'll get one super resolved image. So that's a super clever idea, and that's why it won the Nobel Prize. But what it's doing is it's trading off temporal resolution for spatial resolution, right? So now you get good spatial resolution, but yet it takes a lot of time to get a single image. So if we realize that these are basically variance images, right? Because they're just brightness images, which is the same as variance. So the first thing we did here is to say, okay, let's just estimate the correlation of the images, not the image itself. And then already we could go down from, 12,000 images that you need in Storm, that's the method behind the Nobel Prize. We could go down 2 orders of magnitude to SPARCOM, super resolution correlation microscopy, and we get even a better image. The next step, of course, is also doing learn SPARCOM, which is the model-based AI, but we'll get back to that later. So again, here we're only exploiting the fact that it's enough to estimate the covariance and not the signal itself. And we could get, even better temporal resolution, spatial resolution, but with very good temporal resolution. And we've been collaborating with a group at Weizmann, Professor Giladaran, who's interested in the dynamics of T cells, which is something that you can't see today with standard microscopy. And we've been working together to use these methods to see the dynamics of T cells. And actually what's cool is that this lends itself very naturally to this model-based AI, because we have a very nice model here, but we can also add learning to it. And we've been looking a lot also together with the drug on how we can use this model-based AI for biological imaging. And this is a first example from Gilad's lab. So this is what he gets in the microscope. And this is what we get after super resolution. Of course, I'm not going to go into the biology here, but the thing is there's no ground truth, right? So how do we know that what we're getting is good? And the answer is, of course, we don't. But the nice thing is that Gilad's group had a series of papers in Nature on their prediction of what happens in T cell dynamics. And of course, we didn't know that. He just gave us the image, and we did our processing, gave it back to him. But lucky for both of us, it kind of coincided. So that doesn't mean it's true, but at least it gives some sense of that. Hopefully, what we're getting is meaningful. And the nice thing here, this is based on model-based learning. But of course, when I say learning, there's no training data. Okay, so everything the learning is done from the predicted model. Okay, there's no training data because of course there's no ground truth here. Okay, so that's kind of what we were doing in microscopy. Just very quickly, going back to ultrasound, our lab is working on a clinical application, so we were very interested on, besides maybe using that for pathology, could we do something clinical with that? And that brings us back to ultrasound. So in ultrasound, you don't want to inject fluorophores into the body, but we could inject contrast agents, right? Which is done anyway. It's used to improve contrast. That's not what we're interested in. We want to improve resolution. But these contrast agents are kind of flowing through the bloodstream, and they're very similar to fluorophores, right? We could kind of do the same trick, right? We could estimate the covariance by using these model-based AI. And what that allows us to do, so this is a clinical study we did with Beilinson Hospital on patients with breast cancer. And what you can see over here, these are the ultrasound images, how you would see them on their device when they're scanning. And these are the same images after using this model-based AI. They are contrast agents here, you just don't see them. And here we could localize them, and you can see that, these three lesions that look the same over here are actually very different. So this is actually a benign tumor because it's very homogeneous. This is a cyst because it's full of fluids, and this is a malignant tumor. So this is kind of a nice area where we can show that these ideas could carry over to clinical applications as well. Okay, so I think I'm running out of time. So let me just, give the highlights here. I'm really trying to talk slow, and then I'm like, the downside of talking slow is that I don't get through my slides, but hopefully people could follow. Okay, so let me just highlight the main ideas here in quantization. I think I really explained the main idea before. Since we're quantizing, we're going to lose error anyway, and the question is if we could combine sampling rates and quantization rates and not analyze them separately. So this goes back to work that we did several years ago with Andrea Goldsmith's group. And it started as theoretical work. Could we get rate distortion theory that takes into account both sampling and quantization? And I'm not going to go through the information theoretic aspects. We could get analog rate distortion curves that kind of describe the effects of doing both sampling and quantization. But the important thing for us in practice is saying, okay, for a given bit rate, I'm going to tell you how many bits I'm willing to give. Could I go below the Nyquist rate and just assume that the error is going to be part of the error of the quantization? And what this graph shows us is that you can do that. So for any given bit rate, I could plot the optimal sampling rate when I look at sampling and quantization together. And of course, for flat inputs, there's nothing to be gained. But for any input that's not flat, we can actually get very low rates, well below the Nyquist rate, without losing anything. Okay, the performance of the system is the same. And the other nice thing is that we can now get finite rates even for signals that are not band limited, like the scale marker process. So it's not band limited, but still for every given bit rate, we could sample it at a fixed sampling rate without losing anything. That's the best we could do. If we would go beyond it, we wouldn't gain anything. Now, of course, the drawback is that just like any rate distortion theorem, these are just bounds. It doesn't tell us how to achieve it in practice. So the next thing we looked at, and this goes back to these combining ideas, is, could we actually achieve these low bit rates in practice? And the way we did it is, again, using the same notion that we keep on coming back to, even though, again, there's no sparsity here, is this notion of, okay, to achieve these low rates, what we do is we take our input, we design a combiner, we mix the information, we then use simple scalar quantizers. Okay, so there's no fancy encoding here. We use simple scalar quantizers and of course design the post-processing. And we can show that when we design this for particular tasks, we could actually achieve those rate distortion curves that are much lower than standard rate distortion curves. Okay, so we can sample at lower rates, we can quantize even all the way down to 1 big quantization, and still get the optimal rate distortion curve. And the reason we can do this is because, first of all, we're designing a combiner, we're mixing the information before the low bit quantization. And two, this is, per task, okay? So I'm not saying I could perfectly recover the inputs, it's just that I'm not interested in the inputs, I'm interested in the task of the system. Okay, so we have a lot of work kind of in this direction. We've used this in MIMO systems in order to reduce the number of RF chains, and in each RF chain to reduce the number of bits. So again, all these movies are on my webpage, so you can take a closer look at that. The other thing that I want to point out is that, in everything I've shown until now, we've been doing the mixing using analog hardware, right? We've been building dedicated boards in order to do the mixing. The other thing we've been looking at more recently is using metasurfaces to do that. And there's been, of course, a lot of interest in metasurface for different communication problems. Just most people have been looking at metasurfaces in a passive environment, right? To shape. And I saw a great demo of that this morning, right? To shape the environment. Here, we're looking at metasurfaces as active elements, for example, in a receiver, and we can use them in order to reduce sampling rates and bit rates, or we could use them for active beamforming. So we're not just using them as passive to shape the environment, but rather to really affect the receive chain and the transmit chain. An area we've been looking at them a lot is in 6G networks at near field communication. So, as the frequencies increase and the number of antenna elements increase, This will bring us to the near field, and there doing clever beamforming is really important. So again, we've been using meta surfaces for that purpose. And just to end this part, what we can show is that by exploiting the properties of near field, and this is very similar to what we're doing also in ultrasound, we can actually, even though the math is more complicated, once you've done the math once, you can show that you could get many advantages. So for example, instead of just having like beam steering, where we could steer in a given direction like we have in the far field, we can actually do beam focusing, where we could separate users along the same line. So that's an advantage we could get if we go through these near field equations and do pre-shaping at the transmit. Okay, so I think this ties in also to a lot of the beautiful stuff that Joseph is doing with the different types of beams. But the beam steering at the input is very important, and this goes back again to this pre-coding idea. Okay, mixing the signal in order to get these benefits. Okay, so let me skip through this. We've spoken a lot about how we could do, efficient comm, efficient radar. The next natural progression is putting them together, and there's been a lot of interest in the community in integrated sensing and communication. So we've been working along on that as well as, putting these ideas together. These are different ISAC systems that we've been developing in the lab. But basically, it's putting together all of the ideas that we spoke about until now, with the additional part of doing joint waveform design. So we've been focusing a lot on the receiver side, but of course, if you know that you want to do both sensing and comm, then you could be more clever in what you're actually transmitting. So basically, we're combining everything we showed until now with different designs on the waveform. So let me skip through that. We have several demos that we did in this area, but again, it's really kind of putting together the different ingredients that we had until now with clever beamforming on the transmit side. All right, so that leaves us about 2 minutes, which is fine. I wasn't going to spend a lot of time on this anyway. To talk a little bit, I mentioned model-based deep learning several times throughout the talk, and that's kind of the last component where we really want to put models in, even in problems that are purely data-driven. So I think everyone here knows that AI has taken over many applications. I don't think we need to motivate that here, but I do want to emphasize that most of the areas where we see tremendous usage of AI are problems that didn't have really good models before, right? Like speech or vision, and also where there's a tremendous amount of data. Okay, so all of the applications that have made highlights and headlines in terms of AI are really problems where there's massive amount of data that we could learn from. But if you think of the applications, and let me skip because everybody knows why AI is good. But if we look at the applications that we're interested in, or the types of things that we've shown in the talk today, first of all, we never have massive data sets. Okay, definitely not in medical imaging, or sometimes we have no data sets, right? And things change very rapidly. So if you look at communication networks, maybe we could collect a lot of data for a particular setting, a particular SNR, but in 30 seconds the SNR changed, and then what do you do with all of that, right? So these are environments that are very dynamic. Training again and again could be computationally exhaustive. The robustness is not clear. So if you design a system for a specific SNR, what happens when the SNR changes? How well does it generalize in medical imaging, et cetera, et cetera. So these are, some of the issues that we care about. And in order to try and overcome that, what we've been working on, and many people in the community have been working on, this idea of model-based learning. So how do we put together, signal processing and communication have traditionally been based on models. It got us thus far, right? We all have phones and computers and, many other devices that worked on models. So the models aren't wrong, right? We may just want to use the power of learning to do better in environments that are more challenging. So, we want a natural progression, not throwing away everything we've done and doing something totally different. So, the question is how to do that. And again, many people have been working on this. In our lab, we've been focusing on two main approaches. The first is unfolding. The second is kind of these data-driven algorithms. I'll briefly outline both of them, and then we'll wrap up. So the idea of unfolding is one that I particularly like a lot. And it goes back to a really nice paper of Greger and Lacoud from over a decade ago. Of course, they looked at it in a different context, but the idea is definitely in those papers. And then, for whatever reason, people didn't follow up until recent years. But the idea is very natural if you come from kind of these optimization formulations. So the idea is that you start with your, you have a problem, you write down your optimization algorithm. This is what we naturally do in, many signal processing and communication problems. You then write down, let's say, 10 iterations of the algorithm. So you have your problem, you choose your favorite solver, let's say proximal gradient descent, just because that's used a lot in applications. And you write down, 10 iterations of proximal gradient descent. So actually at this point, you have a pretty lousy solver, right? Because we know that most of these algorithms need thousands of iterations until they get to a good point. But you're only going to do 10 of them. Okay, so that's not going to work very well. But then what you do in the last step, and this is where the learning comes in that in these iterations, instead of keeping everything fixed, you freeze some of the parameters. Maybe it's the forward model that you don't know exactly, or the regularization parameter, and you learn that from data. And the data could be training data, just like in learning, or it could be data that you simulated from your model. Okay, so this is the basic idea on unfolding. There's been tons of work on this by many groups. This is a recent review we wrote in the focus of imaging. And it's an approach that's super powerful. A lot of the examples I showed before where I said we use model-based learning, it's based on this unfolding concept. The other thing we use, and this is useful for applications where we don't have this nice optimization formulation, and this is, embarrassingly simple, so there's almost nothing to say about it because it's really just a plug-in approach, but it's very useful, is there's many problems, and particularly we've been looking at this in communication applications, where we don't have this really nice principle, optimization formulation and algorithm, etc. But there's a good heuristic, like the Viterbi algorithm, right? It's a heuristic, it's a dynamic programming approach. It's not a solver to a specific optimization problem, but it works really well, right? That's how our problems work. The thing is, there's something in there that requires knowledge. Like in the Viterbi algorithm, you have to compute the likelihood that requires knowledge of the channel. Now, what we say here is, if you don't, let's say in Viterbi, you don't know the channel, rather than replacing everything end-to-end by a deep network, right? Do all the steps like you would have done before and only replace that specific block with the network. And because it's a very specific block, usually you could use a very shallow network. Okay, so there's nothing smart about this, right? It's just a simple plug-in approach. But the nice thing is that it works, quite well. And also because it's simple, it's also easy to analyze. So you can also get theoretical results of that. So just to show some examples, we've used these ideas in many applications. In fact, many of them we've seen throughout the talk. I think I have to wrap up. So let me skip through this. We've used this, in image blurring problems. I'll skip through this. We did some work, even with Google on this. Although again, I'm not a big fan of just image blurring for the sake of image blurring, but we developed this and then we used it for different medical applications, which to us is more exciting. We've used this for signal separation. So going back again to medical, for example, one of the issues in ultrasound is that when you do a scan and you're looking for blood flow, you get very, very strong reflection from the clutter, from the tissue, which is basically clutter. So it's very hard to see the blood flow. And here again, we use these model-based networks to get separation. Now, there's no ground truth here, right? I mean, there's no way to get training data. I don't know what the separation is, but you could see this is all real data, but you could see that, we put in something like this and we get this and this, it looks like it's doing a pretty good job, okay? So it's all self-trained. It's not that we're using training data here. And basically what's compensating for the lack of training is the model. Like I said, we've used this a lot in symbol detection. This is the Viterbi net we did again together with Andrea's group, where we just replaced the likelihood by a network and it works remarkably well. It gives you almost the same performance as Viterbi, even when you don't know the SNR and you don't know the channel. And again, we've applied this to many other problems as well. So I'll skip through the examples. Let me just end. We've used this a lot for COVID-19 and other medical imaging applications. So I'm skipping through all that. I do just want to end with one slide on theory. So, I said multiple times that model-based learning is efficient and it's good. Of course, at least for me, it's intuitively pleasing because we have models and why not use them? So it gives us a systematic way to do that. But the nice thing is that we can actually prove that too. So I think there's a lot more work to be done here. And if anyone's interested, I'm happy to talk more about this. But we have at least beginning of results that show that when you incorporate the model into the learning, you do in fact get systems that generalize better and need less training data than they're equivalent without the model. So here, for example, we showed for a specific type of Lista network, without going into details, that the generalization error is smaller than what you would get from a non-model-based network, but even more importantly, it decays with the number of layers. And that's super intuitive. We expect that the generalization error will decay, but no previous results in learning have actually showed that. They always get something that actually grows with the number of layers. And the nice thing is that because of the model, not only do we get tighter results, but it's actually easier to prove results because of the model. So that was kind of a nice benefit. Again, we could show that we need fewer training samples than you need for a non-model-based network. And again, all of this is intuitive, but it's nice to have the theory backing that as well. So sorry for going a little bit over time. And to wrap up, we tried to show, different examples where if we want to be more efficient in processing the data, we have to take advantage of everything we can, including the task, structure. And this is true both for RF front ends, analog front ends, but also for purely data-driven methods. We spoke a little bit about, new limits we could get in terms of sampling, quantization, and super resolution. We spoke a little bit about engineering research, right, developing new devices. And at least to me, one of the exciting things moving ahead is thinking about, okay, how do we put this together and really build new systems, things we really couldn't do before. And, this is an area I'd love to collaborate with people who know more about the systems than I do. I skipped through all of the technical details so you could find them, in our papers and books. And of course, none of this would have been possible without my amazing group of students and engineers that I have the pleasure to work with. So they do all the hard work, obviously. And of course, my amazing and wonderful collaborators who also, all the good ideas are them. So I'd like to thank them as well. And of course, thank you very much for your attention.
Questions in the room? We're a little over time, but I'm sure Yonina's happy to answer.
Definitely.
I have a question. Most of the works you show that those are all great results about the lower resolution during sampling, although yield to better resolution in the analysis, right? But where we are at in terms of hardware and accessibility to this hardware today, because I see a lot of custom systems there. So what if somebody wants to apply some of these, new sampling technique, sub-Nyquist techniques to our labs experiment, for example?
You're saying, what is it like? What could you buy? What is available?
Basically.
Okay, so really, really good question. Thank you for that. So, okay, the way we do most of the things, like you said, right, is by using available devices and modifying them.
Okay.
It would be wonderful if somebody would go out and design them and build them like a company or something. So that would be wonderful. Actually, I do know of some particular, but I think it's all done for internal use. So there are some companies that I know actually built dedicated chips, mainly defense purposes, who kind of, I was in contact with them, but I don't think it's things that are like just publicly commercially available. But it would be wonderful. Actually, again, I learned this morning that there's a lot of spin-offs here and companies here, which is fantastic. That hasn't been my path until now. So, but it would be wonderful to do. So if anybody's interested in that, I'd definitely be happy. But like you said, today what we're doing is really kind of doing it ourselves. I know there's different labs who also did that, but I'm not aware of something that's just like commercially available. But it would be nice to do that, right? And I think part of that is finding the right application, right? Like going back to, let's say, some of the newer stuff, right? Like the modular or the 10. I think if and this is part of what I'm looking for also, right? If there was like, we have papers about it, we built a board, there's different applications we looked at, but they're more academic, right? Like if there's a good killer application where you say, look, in this application, this is really important, let's build the chip for that application, then you have the chip available and you can use it in other applications as well. So that's definitely something that to me would be exciting to think about, but we haven't done that yet. Okay. I hope I answered your question.
Yeah. No, because Nyquist is used literally in everything nowadays, like
right,
from audio to wireless
right.
to imaging, So anything that gives you the same resolution but a lower computational cost is like a huge breakthrough in my opinion. So
yeah, so yeah, you're right. It would be great to have like something commercial available. We haven't followed that path, but it would be great to do. So.
And sorry, follow up. Is there any software implementation, like even just a simulator for something like that?
Yeah. So that we've done a lot of things. A lot of it is available online. A lot of it we put online. But again, I think it's goes back to this issue of when you say a simulator, is it end to end? Is it just that specific block, what does the rest of your system look like?
Yeah.
So I would say most of the things that, we put online are, of course, just that individual, like modular, okay? So the input output for that block.
Okay.
Less of a system level design online. But it would definitely, we were chatting about this morning, these were the types of things I was excited about when I saw a lot of the platforms that you have here that are open system platforms. So to me, it would be super exciting to think of, maybe some of the things here that people here feel are worthwhile, to think of how to integrate them, even on a software level, like you're saying, because that would already be, so to me, that would be super exciting to do. I'd be really happy to do that. But it has to be, I guess, something that people here find interesting enough and then collaborate on doing that. But I'd be totally, not only open, but excited to do that. So
thank you.
I have a question about trading time and spatial. So you mentioned that in the Nobel Prize winner that they have idea of trading, trying to have better spatial resolution with temporal exposure, etc. So I'm wondering, can we do the similar things as when we actually trying to estimate the spatial correlations? Let's say, can we trade time with I want to have super resolution to get the the spatial correlation within the system?
Yeah. No, I think it would be the exact same thing. It's just the only thing to think about is like when you say trade time, right? Is what role is time playing in your setup? So here, the role that time is playing is that you could basically think of it as more like a point-and-point scan, right? Like they're scanning by taking the entire roster and just doing several pixels at a time. So what I'm benefiting is that I'm doing a lot in each image. I'm actually making a lot of fluorophores fluoresce. Okay, so then I need less time, but I could still get the spatial correlation. So it would be a similar thing, right? Where the way to trade off time with spatial is that in each individual sample that you're taking, you have to have more information. You could get that either by allowing, in this case, we're allowing more fluorophores to fluoresce, or with the contrast agents, we're just allowing them, the blood flow anyway is high enough that we naturally get a lot of contrast in each frame. Or you could do that by mixing. And this goes back to the pre-coding. So if it's a communication setting where I have more control over the problem, I could purposely mix. Okay, but again, the point is that in each time I should have a lot of things happening, not just a small number of things happening, but then the spatial correlation will work itself out. Did that kind of answer?
Yes. Thank you.
So we have a question from the online audience, and Shankar is asking, can we use synthetic data?
Synthetic data for the training, or?
It is not specified.
Okay. So I hope I understood the question. If I understand the question, then it's, I think, could we use synthetic data maybe for the training? Is that how you would interpret the question?
I guess so. Maybe he's trying to.
For training, yeah.
To clarify the model-based training.
Yeah. And actually, that's kind of one of the advantages, right? Is that, and again, I know I went through all of that pretty quickly, but the point is, if we think of how we did signal processing, communication, any of these areas, 10, 15 years ago, what did we do? We wrote down models, we simulated them, in a sense, we did training, right? We just didn't call it that way, but we simulated the system, and then we tested our methods by taking the data from the simulated system. So we're basically doing the same thing, right? We're using the model, we're simulating the system, but because we know that the simulation may not be perfect and the data may not be perfect, we're allowing ourselves to learn. And I think the nice thing is that even though you're using a model, you're simulating data from that model, your learned network is more powerful than what you would have gotten from just the model. So even though it's a little bit of this bootstrapping that's not obvious to begin with, right? Because you could think that if I used a model and I generated training data from the model that I used, that the learning is not going to help me. I'm going to be stuck with the same model. But it's not. It does advance. You do get better performance. So it is done from synthetic data. Of course, if I have training data, I could use it. But most of these applications, you wouldn't really have it. So.
More question on that one.
I'm okay. I mean, whoever needs to go could go, but I'm happy to take questions as long as the schedule permits.
Thanks for your presentation. I was just curious about when you say that in some of your use cases you do not have any ground truth. So for these kind of use cases, what is your evaluation methodology and how you are actually sure that the model-based deep learning technique is working?
Yeah, that's a really, really good question that, obviously doesn't have a really good answer, but I'll tell you what we do. So, if you think of problems of super resolution, right, there's two things you could do. One is you could simulate, and that we do, right? So we simulate simple scenarios like, point sources or things like that. So we could verify that at least in things that we could simulate, we get good results, okay? But those are never going to describe the real world. So if you're looking at, T-cell dynamics, nobody knows how to simulate that because they don't know what's going on in the dynamics, right? So what you could do again is take the same mechanism and try it on simple things that you know the answer to. So you could try it on dynamics that you know the solution. You could try it on point sources. So that's kind of one sanity check. But then for the real thing that you're looking for that nobody has seen before, you really don't have ground truth. And the best we could do is, like I said, verify the system on scenarios that are simpler and that we know we have ground truth, but they're not trained on it. So that gives us kind of like a sanity check. And, correlating with other things people know. So for example, in the T-cell dynamics, there are different predictions about what should happen. And then, we could test that on the result that we get. The other thing is visual. So like in the problem of separating, clutter from blood flow, there is no ground truth. Okay, the body's combined. So there is no way to say this is really what it looks like. But, visually, You, first of all, visually, you could see, you can see the difference between different methods. So you can see they look different. And also there's measures, there's local measures. So, there's measures for clutter, there's measures for blood flow. So you can try them in each one separately and feel like, it's resembling, but there isn't really, it's a really good question and there isn't a really good answer. There's no one thing that I could say, this is how you can do it. Putting what I said together, I think the main way, at least we do it, and maybe there's better ways, is always doing simple simulation, like always looking for simple cases, point sources, simple cases that people figured out in the literature, things like that, at least as sanity checks. And then, trying to correlate with other things we know about the material. But there is
one thing that I was thinking while you were talking about this is that, okay, now you can separate maybe the blood flows in the body. Okay, why then? The step further would be to take a medical decision or act in some sort of automated manner based on that imaging. And so this brings up a lot
that's
of
like a downstream task. And that's what we do. Like we do evaluate on downstream tasks. But that still doesn't mean that our separation was perfect. It just means it was good enough for the downstream task. Yeah.
Thank you.
Sure. I think, was there another?
We've got 2 more questions online, but I think we can everybody should feel free to go.
Sure. And sorry for going over.
The 2 questions online are how are software
How are, again?
software realization
How is the software? So, okay, I'm not, if I understood the question, then there's maybe, so I'll rephrase the question. I hope I'm keeping what whoever asked meant, is that maybe, if we start with the simulator, then why would I get a different algorithm than what I simulated, so to speak? And I think that's what I addressed also before, which is surprising that I do get something different, is that even if I start with, like, let's say I do unfolding, and I start with a convex optimization problem, I simulate the algorithm, and I use, proximal gradient or whatever, but then I do unfolding. On the same data, I will actually get a different, the gradient steps will be different. And that is surprising that even though the data simulated, I started with a well-defined algorithm, when I do unfolding, I will end up getting something different than when I started from. So I don't know if that was the question, but
the last one. This one is interesting. So maybe everybody will be interested. Someone is inquiring. So using some your example, and especially as far as multiple sensors, multiple signal chains, the question is how do you think it affects the overall system cost?
Yeah, that's a really, really, really good question. Yeah. So that's something we stressed out a lot in the earlier days when we were working this. It's a really, really good question. So yeah, of course, all of that, like I shoved under the rug, but it's very important, right? So you want to make sure maybe you're reducing rate, but you're doing something so complicated that in terms of power or other metrics, you're not benefiting at the end. So that's a really important point. So I'll answer it two aspects. So first of all, in terms of sampling, just because we worked on it for many years, and that was a concern, I think not the first way we designed the system, but the way we ended up designing was due to that aspect. And the point there was that the front end that we're using is really low power. So we're using, very simple spreading sequences that are things that people use, of course, at the time, right, for CDMA and things like that. So those were known that you could do them actually at very low power, and all we're doing is a multiplication, which is low power. But it's not trivial because we had other ways of implementing the system that were mathematically totally equivalent, but actually consumed a lot of power in the front end. And we didn't realize that until we started building the system. So that's a really, really important point. And what I showed here was already after we kind of re-optimized for input power. But it is important that not everything that works on paper is actually going to be low power, which brings me to the second more recent example, which was together with Rabia. And I didn't show that here, but we also looked at like the analog precoding for task-based, and together with Rabia from the EU, we actually built it. And there we really had, this was Rabia's insight, but we talked a lot of examples about how the analog precoding. So when we use the CDMA sequences, those were good because those are low power. But when we have a general matrix, just like for quantization, let's say, we just do general mixing, on paper, that's perfect. But it turns out that consumes an enormous amount of power. So even though the fact that we went down from, 10 bits to 2 bits, all the power we saved was all like in the front end of that mixing, okay, which was terribly depressing. But then, so the next step, and that we only learned because we were working with Rabia, who actually builds the chip and knows how to do the power computation. She's like, look, really sorry to break this to you, but you know, this is bad. So then the next step that we did, and that was kind of, I think, the cool part of like learning of the collaboration, was looking at, okay, let's do the reverse. So let's kind of understand what are pre-coding methods that would be cheap in terms of power, and now what do I need to do to the math to make that work, right? Like it's not the standard thing, don't give me sufficient mixing, but now I could combine them maybe in non-trivial ways that I will get mathematically sufficient mixing, but I'm still keeping the low power. And, you know, to me, that was actually the most exciting part of the project was not, of course, the student liked it less. Like, I think he still would have been happy if what he did would have just been implemented. But that was the exciting part, is saying, okay, you know, that's the beauty of the collaboration, is that like what we did is actually bad. But now that we understand the power considerations, we can go back. So I think, sorry, it's a very long answer, but I think I'm just getting excited because this is, I think, where like the collaboration comes into play. So I think once we understand the math and the concept of why it works, and we work together with people who know more about, you know, the power and the hardware, there's always a nice way backwards. But that's where the fun is, right?
Shall we thank you, Nina, for the visit?
Follow up, that's great.
Yeah, feel free.
Stop and say hello.